Hi everyone. I'm going to continue on with our discussion of Galois extensions and the main theorem of Galois theory. I just really want to work through one other kind of interesting example. Okay, so here's the example. I'm going to let f be q. We always pretty much let f be q. I'm going to let f of x be, how about x cubed minus 5? That seems like a good polynomial. It's irreducible. Okay. And I'm going to let k be the splitting field of f of x over q. Okay, so this tells us that k is actually equal to q. Well, I have to adjoin all the roots. I need the third root of 5, certainly. But then I need these two other complex numbers times the third root of 5. That bar on the gamma just means conjugate. Okay. In fact, gamma, you could say, is e to the 2 pi I over 3 if you've taken a class in complex analysis. It's a third root of unity, so it actually corresponds, I think, just to like this element right. Well, I can't draw very well. But this should be a third of the way around the circle. Okay. If you're drawing your complex numbers, here's the imaginary axis and the real axis. Okay. And you might actually write k a little bit more compactly. I'm actually going to write 5 to the 1/3 instead of the cube root of 5 just because I think I'm less likely to make mistakes. And I also am going to have gamma right here. Because if I have a field that contains the third root of 5, it definitely contains and the third root of 5 times gamma. Well, because it's a field, I can divide by the third root of 5, and I'll just be left with gamma. And once I contain these two, I'm going to pick up third root of 5. I'm going to pick up third root of 5 times gamma. And gamma bar is just gamma squared in this case. So that's the picture. Okay. I want to understand this Galois group. So I want to understand ought k over f. Okay. This extension is Galois. So the size of ought k over f is equal to the size of it's equal to the size of k over f. And if you do a little bit of computation here, this is equal to the size of k over q adjoin 5 to the 1/3. Okay, times q adjoin 5 to the 1/3 over q. This one right here is definitely degree 3. I'm just adjoining a root of x to the 5th minus 3. And this one right here, if we think about it just a little bit, this one actually has to be degree 2. And the reason it has to be degree 2 is if we, how do I put this, is that gamma is a root of, all right, x cubed minus 1, and that's x minus 1 times x squared plus x plus 1. Remember, this one right here is irreducible. And gamma is definitely not a root of x minus 1, so it's got to be a root of this irreducible one right here. So that's why this one right here is degree 2, because these two fields are not equal. This one has some k has complex numbers, this one doesn't. And so they're not equal, and the thing we need to adjoin to get from one to the other is a root of a quadratic polynomial, so it's got to be 2. Okay. All right. So I know that ought k over f has order 6. Because that's 2 times 3. 2 times 3 is 6. Okay. So ought k over f has order 6. And I can write down 2 elements in it. How about I call them sigma? Well, and let's see. Let's say I want sigma. Any element of k over f is completely determined by where it sends 5 to the 1/3 and by where it sends sigma. And let's say, where it sends gamma. Let's say it sends gamma to gamma, and let's say it sends 5 to the 1/3 times gamma times 5 to the 1/3. And let's say we have another element here, let's call it, I don't know, phi. And phi is going to send, how about we just fix 5 to the 1/3, and we're going to send gamma to gamma squared, which is also the conjugate of gamma. Okay. Remember, any automorphism can only send 5 to the 1/3 to 5 to the 1/3 gamma times 5 to the 1/3, or gamma squared times 5 to the 1/3. There's only 3 possibilities there, and it has to send gamma to gamma or gamma bar, which is gamma squared. And so there's only 6 possible automorphisms. That way we found them all. All these things are fine. I'm just giving names to 2 of them. Okay, so these are just 2 important automorphisms here. All right. Let's think what we can. Sigma squared, well, what's that going to do? Sigma squared is going to send 5 to the 1/3. Well, first it's going to send 5 to the 1/3 to, first when I apply 1 sigma, it's going to send it to gamma times 5 to the 1/3. But then it's going to send gamma to itself, and 5 to the 1/3 to gamma times 5 to the 1/3, so we'll end up with gamma squared 5 to the 1/3, and of course it's going to send gamma to gamma and gamma to gamma. So gamma squared does that right there. Sigma squared does that. Sigma cubed, however, if you do this again, well, this is going to send 5 to the 1/3 to, I'm just going to pick up another sigma. It's going to be sigma cubed times 5 to the 1/3, and that's just 5 to the 1/3. It's going to send gamma to gamma. And so sigma cubed is the identity. Okay. On the other hand, phi squared is going to send 5 to the 1/3 to 5 to the 1/3. And it's going to send gamma to gamma bar. And it's going to then send, or, you might also write that as gamma squared. And it's going to send gamma squared to gamma squared times gamma squared, which is gamma to the 4th. And since gamma cubed is 1, this is gamma to the 1, or just gamma. And so phi squared is also the identity. Now I'd like to do a couple quick computations of sigma composed with phi and phi composed with sigma. Okay. Need a little more room, I think. Okay. So sigma composed with phi. Well, the phi part is just going to send 5 to the 1/3 back to itself. And then the sigma part is going to send it to gamma times 5 to the 1/3. On the other hand, phi will send gamma to gamma squared, and sigma will just send gamma to itself, so it'll also send gamma squared to itself, so this will just be gamma squared. So sigma composed with phi is this. All right. It gets a little weirder now. Because now if we do phi composed with sigma here, it's going to send 5 to the 1/3 to, well, sigma is going to send this to gamma times phi to the 1/3. And gamma times phi to the 1/3, so this is sigma. Now I'm going to do gamma. It's going to leave the 5 to the 1/3 alone, but that's going to send, oops, it's phi. Gamma to gamma squared, 5 to the 1/3. Okay. And gamma, well, it's going to do something similar. Sigma is just going to send it to gamma, and phi is just going to send it to gamma squared. But I want you to notice something. Sigma composed with phi is not equal to phi composed with sigma. They are different elements in the group. So G is not, in this case, abelian. All right. I want to identify all the subgroups of G I can. Okay? G has order 6. So it can have subgroups of order 2 or 3. Interesting subgroups. I don't care about the identity of G itself, right? Because the size of the subgroup has to divide the order of the group. Groups of order 2 or 3 are cyclic, since 2, 3 are prime. Remember, any group of prime order is cyclic. Okay, so I think we can actually write down all the different elements of G in terms of our generators. So we always have the identity in any group. Then we have sigma. We have sigma squared. Sigma cubed will just get us back to the identity again, so we don't need to write down that. We have phi. Phi squared would just get us back to the identity again, so we don't need to write that down. We have sigma composed with phi, and phi composed with sigma. And this is all the elements of the group, because we know we have to have 6, because that's the size of the extension. Okay. The subgroups are, drum roll please. The subgroups are, okay, call H1. This is ID sigma sigma squared. H2. This is ID phi, that's a cyclic subgroup. H3. Okay. ID sigma composed with phi. Now it turns out that sigma composed with phi, if you do it twice, what you're going to get is the identity. Because what we're going to get is if when we do it twice, the 5 to the 1/3 will get sent to here, right? And then that'll get sent to, well, the gamma is going to get sent to gamma squared, 5. And then we're going to get the 5 to the 1/3 is going to get sent to gamma 5 to the 1/3. And that's just going to be gamma cubed is 1. And likewise, if we did this twice, we're going to get gamma gets sent to gamma squared. Gamma squared is going to get sent to gamma to the 4th, but gamma to the 4th is gamma. So if we did it twice, another sigma composed with phi, we're just going to get the identity. And likewise with the other one. And so H4, this is phi composed with sigma. Okay, these are the interesting subgroups. Corresponding to these, we should get 4 interesting subfields. So what we're going to have now is 4 subfields. Now this is over K, which is Q adjoin square, 5 to the 1/3 and gamma. And what are these four subgroups going to be? This is maybe a little bit not obvious. One of them is definitely going to be Q 5 to the 1/3. That's a degree 2, that's a degree 3 extension of Q. Another down here is Q adjoin gamma. And this one is actually the same as Q adjoin gamma squared, because remember, gamma squared squared is gamma, and gamma squared is gamma squared. Okay, so these are actually the same. And this one right here, well, it turns out that this one is Q adjoin gamma times 5 to the 1/3, and this one is Q adjoin gamma squared 5 to the 1/3. And each one of these should be K fixed by each one of these subgroups. So let's see if we can figure that out. Okay. One of these is not like the other. That's this one right here. Because in each one of these other groups, all we're doing is we're adjoining. So these three are adjoining a root of x cubed minus 5. This one's not. That's different. Okay? So that's adjoining a root of 5. Let me just connect those for you here. And this one is adjoining a different kind of root. So these look all very similar. That one's a little different. One of these groups looks a little bit different. That's this sigma squared. And I think if you go back to the definition of sigma, right here, I think you immediately see that sigma is going to fix gamma, but it's not going to fix any of the roots. So KH1, that's Q adjoin gamma. Okay. Now let's look at KH2. KH2, we have to look at the things that are fixed by phi. And if you remember, if we flip back to our definition of phi, phi fixes 5 to the 1/3 and it messes with gamma. So I think we're going to get KH2 be Q adjoin 5 to the 1/3. Now, what about KH3? Well, now we have to figure out what is fixed by what is fixed by sigma composed with phi. Okay, so let's go back and look at our sigma composed with phi. Okay, sigma composed with phi, well, that didn't fix gamma, it didn't fix 5 to the 1/3. But let's compute what sigma composed with sigma composed with phi. What does that do to, well, why don't we just try one of them? It's going to fix one or the other. Okay. This is, when we computed this earlier, this is going to be gamma squared, okay, gamma times 5 to the 1/3. And that's equal to 5 to the 1/3. These two are not equal, so it didn't fix it. Let's try the other one. That's equal to, okay, now, phi sends gamma squared, as we've seen, to gamma to the 4th. That's just gamma, because gamma cubed is 1. And sigma is going to send the 5 to the 1/3 to gamma times 5 to the 1/3. And look, lo and behold, this is gamma squared times 5 to the 1/3. All right. And finally, the only other possibility is KH4 has to be Q adjoin gamma times 5 to the 1/3, and I'll let you do the computation on that one. But I think by elimination, we've already seen that's the only possibility. Okay, so I'm just illustrating yet again this main theorem of Galois theory. The fixed fields correspond to the subgroups, or the intermediate fixed fields correspond to the subgroups. Okay, that's it for here. I will do maybe one more brief video tonight.